Good day, students. Welcome to math.serve.com. In this clip, we're going to be going over problems 21 to 27 of the Algebra 2 Regents January 2015 examination. All right, let's take a look at problem 21. It reads, the domain of f of x equals -3 over the square root of 2 minus x is the set of all real numbers, and then we pick one of these options. All right. So one thing you want to note is that when you're solving problems involving domain, you want to watch out for square roots and rational expressions. Okay. Whatever input value causes the denominator of a rational expression to be 0, or anything that causes the radicand to have a negative value should be excluded from the domain. Okay, so just remember, number divided by 0 is undefined, and the square root of a negative number is undefined. In this case, we have a combination of both situations. We have a rational expression with a denominator expression, and we have a radical. Okay, so we're going to be combining the restrictions on these two cases to find the domain of this function right here. All right, so these are the steps we're going to use to solve this problem. First of all, we're going to set the denominator to not equal to 0 and the radicand to greater than or equal to 0. We're going to solve both equations, and then we're going to unite them together. All right, so let's go ahead and get started. So we're going to start with the rational component. So in order for a function to be defined, in step 1, the denominator, which is the square root of 2 minus x as a whole, cannot attain the value of 0. If it does, you'll be dividing by 0, and you have an undefined output. And the argument of the square root, the radicand, must be positive. So 2 minus x has to be greater than or equal to 0. You could take the square root of 0, and you can take the square root of a positive number. If it's negative, then it's undefined. You have an imaginary output. Okay, so let's solve these two equations and unite them together. So for this one on the left side, we'll square both sides of our equation. Square that, square that. That yields 2 minus x cannot be 0. And then you can subtract 2 from both sides. You have negative x cannot be negative 2. Divide both sides by negative 1. And then you have x cannot be negative 1. I'm sorry, x cannot be positive 2. All right, minus over minus is plus, and that divides out also. So what does this mean? If x is 2, you will have a 0 in the denominator, which results in an undefined output. So this value must be excluded from the domain. All right, and then in this case here, let's solve this inequality. We can subtract 2 from both sides of our equation. That yields negative x is greater than or equal to negative 2. Now, the only difference between solving equations and inequalities is that anytime you divide by negative, the order of the inequality changes, whereas that's not applicable to an equation. Okay, so we divide both sides by negative 1, and what do we have next? We have x is less than or equal to positive 2. Okay, so you see how I reverse this inequality here. All right, so the left equation tells us that x cannot be 2, and this equation on the right said x can be 2 or greater. Now, if we combine these two together, what do we have? This says no 2, this says 2 or greater. So if we combine them together, we just simply have to eliminate 2 from the domain because this left equation says that it must be excluded. So if we unite these two, we're going to have x is less than 2. That is our domain. Okay, so this is our domain. Answer is option option number 2. All right, let's take a look at problem 22. It says, which equation could be used to solve 5 over x minus 3 minus 2 over x equals 1? Now, one thing you want to note when solving rational equations um, is that whenever you're solving rational equations, multiplying both sides of the equation by the LCD clears out the denominators. Okay, that's a very effective way of solving rational equations. Now, the steps we're going to use to solve this problem are as follows. First of all, we'll find the LCD of the denominators. So we have x minus 3 here, x, and then we could put a 1 here. We'll find the LCD of those three expressions. Step 2, we will multiply the equation by the LCD. Why? Remember what we said earlier? When you multiply a rational equation by the LCD of the denominators, it clears out the denominators. So if we multiply by the LCD, all the denominator expressions will drop off. And after that, we will set up the equation in standard form. It's going to result in a quadratic. We have an x and an x here, so it will result in a quadratic. We'll express it in standard form because all our options are in standard form. All right? Okay, let's go ahead and do it. So step 1, let's find the LCD. The LCD of our denominator expression. So what is the LCD of x minus 3, x, and 1? They are all coprimes, so the LCD is simply the product of the three expressions, x minus 3 times x times 1. Okay, in this case, I won't expand it completely. I'll show you why in a reason. I'll just leave it like this, x minus 3 times x. Now, step 2, we want to clear out the denominators. Okay, so we'll rewrite the original problem, 5 over x minus 3 minus 2 over x equals 1. Now, what are we going to do? We're going to multiply every single term by the LCD. So we have x minus 3 times x, and then this one times x minus 3 times x, and then this term times x minus 3 times x. Okay, what happens? Check this out. This x minus 3 divides with that. X minus x divides with this x, and that stays alone. Okay? We shouldn't be surprised at what happened because we're multiplying by the LCD. Every single denominator is going to be a factor of the LCD, okay, by definition. All right, now let's simplify what we have. 5 times x is 5x minus, now we're just going to distribute this 2 to the x and then negative 3, okay? Don't forget you have a minus here and a minus here, so you have to be really careful when distributing negative numbers. So we have minus 2x plus 6. Okay, it's very easy to make a mistake here. And then over here, we just distribute the x to the 3 and the x. Don't bother with the 1. It is a multiplicative identity, so it doesn't change anything when you multiply 1 by it. So we have x squared minus 3x. Now, what have we done so far? You notice we have eliminated the denominators. That's the beauty of multiplying by the LCD. Lastly, we'll just write this in standard form, combine like terms, and we will be done. So let's see, what can we do here? We can combine, do some combination. 5x minus 2x is 3x plus 6 is equal to x squared minus 3x. And then just subtract 3x from both sides and subtract 6. Subtract 3x and subtract 6. And that will give us x squared minus 6x minus 6 equals 0. We're not solving it completely. So our answer is option number 3. All right, let's take a look at problem 23. It reads, how many distinct triangles can be constructed if measure of angle A is 30, side A is root 34, and side B is 12? Now, one thing you want to note when solving SSA or ASS triangles with the law of sines is that you can have no, one, or two triangular set of solutions. All right. And another thing to note is that when solving these cases, sine can only be 1, -1, or everything in between. 1 and -1. Those are the only values sine of an angle can attain, if you remember your sine function. And the sum of angles in a triangle always adds up to 180. All right, so if any of these two conditions are violated, then you know that that is not a triangular solution. All right, so the steps that we're going to use are as follows. We're going to draw and label our triangle. And then we're going to go ahead and solve using the law of sines to see the number of solution sets that there are, okay? There are many ways you can solve problems like this. There are some formulas you can use to calculate exactly the number of solutions. Personally, I think the best way is just try and solve the problem. When you run into problems, into troubles, if you execute your algorithms correctly, more likely than not, you have arrived at a solution that's not a part of the solution. Okay, you've arrived at a triangle that cannot be constructed. All right, so we are just going to start this problem and solve it blindly, basically working to see where it takes us. Okay, are we going to have two solutions? Are we going to have one or no solutions? And of course, if we have one triangular solution, we have to further classify it into acute or obtuse. Acute basically means that the angles um, are between 90 and between 0 and 90, and then obtuse is basically angles between uh, 90 and 180. Okay, if you have one angle that's between 90 and 180, then you have an obtuse triangle. Then you have acute if all the angles are between 0 and 90 degrees. All right, so let's go ahead and solve the problem and see what we get. All right, so step number one, we're going to draw and label our triangle. Now, labeling the problem correctly is extremely important, okay? If you do not label it correctly, it's like you're building your house on a faulty foundation. Your structure will crumble. So we want to make sure that our labeling is correct. What do I mean by correct labeling? So I'm going to call the vertices A, B, C. Notice we're provided with A and B here, so that's a clue. Now, the side opposite uppercase A must be lowercase a, opposite uppercase B must be lowercase b, and then the C's in that orientation. So this is what I meant by accurately labeling your triangles. All right, the pairs of letters must match. Uppercase are the angles, lowercase are the sides. Okay, so measure of angle A is 30 degrees. This is 30. And then side A is root 34. And then side B is 12 units long. Okay, let's go ahead and put that in. Side B is 12 units long. Okay, now what type of problem is this? Can we use law of sines, law of cosines, Pythagorean theorem, SOHCAHTOA? Well, if you take a look at this situation right here, if you notice you have a complete pair, angle on a side, and an incomplete pair. Anytime you have that situation, you always use the law of sines. Okay, but if you have SSS or SAS, then you use the law of cosines. All right. So what kind of law of sines problem is this? We have side, side, and angle. Okay, SSA. All right, SSA. Anytime you see SSA or ASS, what should you keep in mind? This is an ambiguous situation or an ambiguous case, okay? Ambiguous case. What does that mean? It means that you're not guaranteed to have one unique solution. You could have one unique solution, but you could have no solutions, or two triangular solutions. That's where you have the ambiguity. So you have to always watch out for SSA triangles. Okay? All right, so with that in mind, we shouldn't be surprised if we are seeing interesting things happening. So we're going to start off by finding the pair that's incomplete, and then we can advance from there. The incomplete pair is B, so we're going to find uppercase B, which is the angle. All right, we're going to use the law of sines. Sine of big B, I like to start with what I'm looking for, divided by lowercase b equals, now the next ratio must be complete. Remember, if you have one equation, you must have, you can only have one unknown to solve for, you can only have one equation to solve for one unknown. All right, so sine B over B is equal to sine big A over little a. If we substitute the values here, we are going to have sine big B is equal to little b, which is 12, equals sine big A is 30 divided by little a, which is rad 34. Now, what do you notice about this equation that we just set up? It has only one unknown, namely uppercase B. Okay, so that's how you know that you set up your problem correctly. Okay, so we're looking for big B. Let's go ahead and advance. We multiply both sides by 12. Put a 12 here. Always put the number before the trig functions. Some students put the 12 with the angle and they multiply them together, and, or put it in the calculator in that orientation, and then it ruins the whole thing. So put the number before the trig functions, please. Okay, so the 12s cancel out. And then you have sine B equals 12 sine 30 divided by rad 34. Now remember what we talked about earlier. We said sine can only be 1, -1, or everything in between. Okay, so just to illustrate with a number line, the sine function can only attain values at the boundaries or interior of the interval from -1 to 1. All right, so this is the range of the sine function. So it goes from -1 all the way to 1 and everything in between. Okay, so if you take a sine function and you get an output like 5 or anything bigger or less than -1, bigger than 1 or less than -1, uh, that's out of the domain. All right, so let's go ahead. If you plug this into your calculator, you have sine B equals 1.02899. Now, is this feasible? The answer is no. Okay. Um, since sine B is outside the domain, that means you have absolutely no triangular solution. All right. If you try to do this blindly, let's say you plug this into your calculator, you get a domain error, which also tells you that this is not a triangle you can draw. Okay. So let's go ahead and write down a real quick remark. So since sine B, sine of any angle, must be must be 1, -1, or in between. There is no triangular solution. Okay, no triangular solution. The conditions were violated really early in this problem. So our answer, if you go to the options we have, our answer is option number 4. There is no triangle you can draw with these given measures. All right, let's take a look at problem 24. It says the expression 3 over 2x plus 1 quantity times the quantity 3 over 2x minus 1 minus the quantity 3 over 2x minus 1 square is equivalent to. So one thing you want to note is that the difference of squares is different from the square of a difference. Okay? So a squared minus b squared is a difference of squares. A squared minus b squared is a plus b times a minus b. It is not a minus b squared. Okay? So in this problem here, On the left side, you have the factored form of a difference of squares. On the right side, you have the square of a difference. They are two entirely different things. All right, some students might think these two are the same and pick option 1, and that is incorrect. The steps we're going to use to solve this problem are as follows. We're going to find a GCF of these two terms on the both sides of the minus, factor it out, and then simplify and see what our final result will be. Okay? All right, so step number 1, let's go ahead and factor out the GCF. We have 3 over 2x plus 1 times the quantity 3 over 2x minus 1 minus 3 over 2x minus 1 square. Okay, so this can be written further into 3 over 2x plus 1 times 3 over 2x minus 1 minus, if you square it, means you have two copies of this quantity being squared, so 3 over 2x minus 1 times 3 over 2x minus 1. Okay, not minus and plus, please be careful. The same thing twice. Now the GCF is 3 over 2x minus 1. That's the greatest common factor. We'll go ahead and factor that out. We have 3 over 2x minus 1 times what we'll have left is this term right here and this term right here. Okay? When we factor out these two, it's as though you're dividing. Okay? And then we're going to be left with quantity 3 over 2x plus 1 minus quantity 3 over 2x minus 1. All right? So what we are going to do is simplify. First thing is, do not forget to distribute this sign to both terms in this parenthesis. So 3 over 2x and negative 1, we'll get an even distribution of the negative sign. So we have 3 over 2x minus 1 times 3 over 2x plus 1 minus 3 over 2x. Minus times minus is plus, so please be careful with that. Plus 1. Now, combining like terms, 3 over 2x minus 3 over 2x would add up to 0. And then 1 plus 1 is 2. So we're going to have 3 over 2x minus 1 times 2. Now distribute the 2 to both terms in this quantity here. And that yields, now how do we multiply this? You can write this as 2 over 1, okay? We're multiplying it with 3 over 2, so you don't make any mistakes. If you do that, you're going to have 2 times 3 is 6. 6 over 1 times 2 is 2. 6 over 2x minus 2 times 1 is 2. 6 over 2 is 3. 3x minus 2. So there goes your final answer. Our answer is option number 4. Yeah, I think we're going to stop here and continue this later. Thanks so much for taking the time to watch this presentation. We really appreciate it. If you found this tutorial beneficial, feel free to give us a thumbs up. We'll appreciate your positive feedback. Do subscribe to our channel for updates to the remainder of this review series and other cool math tutorials. If you have any questions or need support getting ready for the Algebra 2 Tricks section of the Regents exam, just place your questions in the comment section below, and we'll be glad to address it as soon as we can. More clips can be found on mathgotserved.com. Thanks again for watching.